welcome to everybody who is joining the meeting. Obviously, you have a lot of interest in this topic, and it's actually a lot of interest all over the country because everybody is worried about that, what they need to know, what they need to do, and all other things. And also, there's a lot of private vendors that they're providing these services. There are a lot of myth, and I will try to at least give you my perspectives, and then at the end we will address your concerns, your questions, and all other things that needed. I hope you can hear me. You can see my screen, and so um, I'm in Chicago. It's a beautiful city. It's relatively cooler than rest of the country because of the big lakes. Northwestern is just next to the lake. It's actually in this part here, and it looks like a lot of interest. At least quite a few people are attending in the meeting. So let's get going. I don't have any conflict of interest. I'm not paid by anybody. I'm just want to declare that. So what I'm going to talk in this my presentations is the why machine commissioning is needed, what resources you need, what are the equipments, what are the issues with the golden or reference data. I'll talk about a little bit pros and cons. What is the time requirement? What is happening with the modern machines, benchmarking, and all. And at the end, I will talk about some conclusions, some take-home messages. And so the preface is that why we need to commission the machines, obviously, and then in that context, the only document exists today is the TG-106. So, it's relatively it's an older document, but it's still fairly good document to read. So what do we do in radiation oncology? The process, the commissioning, you buy a machines and then you are given these machines and you are supposed to commission. So before we go to the commission, there is another term which is called the acceptance testing, ATP, acceptance testing process. That is done with the help of engineers. They set up the machines and all other things. But then once they hand over the machine to you, then you are supposed to commission, or you're supposed to give it to somebody else to do the commissioning. What they do in commissioning, obviously, they collect a lot of data. They do PDDs, profiles, and a lot of manual data, the S sub C, S sub CP, wedge factors, stray factors, MLC, and there's a slew of the thing. So what do you do with this commissioning data? Obviously, they become your reference point for your future use. That's one thing. The other thing is that these data goes not exactly the same data sets, but these data goes in your treatment planning system. So the TPS modeling these days, especially the advanced treatment planning processes, they don't require all the data you collected. They take a sample data and then they model just to verify their algorithms. And then that one becomes a big process. This one is actually a black hole. It's very hard to understand, but that is the process. So the data goes for the modeling, a part of the modeling. So in the modeling process, obviously, you're commissioning a treatment planning systems. And in this one, I say TPS type B and C. The type A treatment planning systems, they exactly use your data, like old 30 years old treatment planning systems. You put the data, they interpolate, and then they calculate all the things. But that is a passe. That is no longer used. Now, the modern treatment planning systems, they are the model-based, and that is the type B and the type Cs. Type Cs are the more advanced that they are very close to the Monte Carlo. So for the B and C type of treatment planning systems, they are modeled and they are only sample data which are used. Then what do you do from there onward? Well, there onward, then you're going to do is the validations. You have already collected data. Now you have a model, and now it's spitting out the informations. Then you are going to again verify, or you can call it the validation. So you're going to do the point in 3D, obviously central axis, half axis, and all other things. You're also going to verify your dose calculations are right, isodose, DVH, clinical cases. In that situations, MPPG5A will provide you some information about the homogeneous and heterogeneous. Obviously, you may not have a heterogeneous phantom, but at least you can try some cases with the lung and carc. And then the final things you're going to verify is patient-specific QA passing rate. With all that things, whether you are going to meet, whether you are meeting that your passing rates. If you're not meeting, that means something is wrong here, or you didn't take the proper data. So imagine you took the data, model, and then you're validating. So it's the process. That's how you're going to do that. Now, we are going to just go back in time. This was International Atomic Energy. They did some surveys. It's obviously 24 years old, the document. And they provided informations that what are the problems, where they found the errors. In this particular document, they found that there are a lot of scenarios, and I'm just going to give you some specific events. During the installation of linear accelerators, the physicist, he found it that there was an 8% discrepancies between his measurement and the manufacturer, the one which they quoted. So 8% the physicist found. And physicist, he thought that it was his error. Manufacturer's data was correct. That's what he thought. But that was not true. And actually, the physicist's data was correct and manufacturer's data were wrong. And so you have to be careful to conclude that whose data is correct and whose data are not correct. So that's just something anecdotal. I want to give you this information. There is another document. It was 2008. It was written by WHO. Obviously, you may be wondering why WHO is in radiation, but they wanted the risk profile. They want to just know how much errors are made in radiation oncology. And they provided a very large data sets. They collected data from 76 to 2007, and they took the 3,125 adverse events. Adverse events is like accidents, like big errors. And when they look at these big errors, and then they divide into various categories. And if you look at the various categories, then they actually provided. But let's take the where it matters. The first thing it comes to us is that the commissioning data becomes critical. And commissioning data, you can see that there were 750 incidences that the commissioning data were either inaccurate or they are okay. Then the next highest probability of errors are planning. Obviously, these days, if you have done the proper things, you do double check, and then that's a process that dosimetrist and you manage that one. The other problems that time was that the treatment informations are not transferred properly. Well, these days, that also happening is a possibility, but it's seldom. It's not that. Treatment delivery errors are also there, and then there are many, many other things, but they're not important. The important thing for you to think about, again, is the commissioning and planning. Those two are the major ones that we need to concentrate. So let's now talk about the commissioning. What happens that when people take data, this is uh, data from Sweden, and they compared 9 machines from one institutions. Obviously, these are from the different vintage, and they compared all kind of parameters. So looking at the small fields, looking at the low energy, high energies, large fields, and again high energy. So this is low energy, high energies. And you can see here that the data of 9 machines are split into two sets, one here and the other one is here. Obviously, these are the percent deviations, -2% and -1%. And obviously, as a beam commissioning time, these becomes -1 or -2%. I think this becomes significant. And we'll come back to what should be your criteria. Obviously, you can see that for a small field and large field, the high energy beams are deviating. Actually, it turned out to be the 6 MV beam or the low energies. The beam parameters, they do not change from machine to machine and also from manufacturer to manufacturers. Actually, these days, so you could trust the 6 MV data fairly good. Now, there is another data from Glidehurst. She actually compared between 5 institutions. So she compared from that time she was at Henry Ford, Southwest, Colorado, Dallas, St. Louis, uh, and they compared all the true beams. This is true beams again, and they compared the data. Very good paper to read. It provides you a lot of information. And the result of this particular document is that they compare. I'm just going to highlight only a few things here, and they compared that the standard deviations between 3 institutions are 0.2% of all LINAC. So between all the true beams, the differences are 0.2%. When they compare the 6, 10, and 15 MV beam qualities, that differed only between 0.3%. Compared to the previous paper that I showed you, that significant deviations were there, but here in this paper, 6, 10, and 15 MV beam, the differences in percent depth dose were only 0.3%. Rest other things are also within 3%. So that is very, very good to know that depth dose and these things are within 0.3% between multiple institutions of the same vintage, which is a true beam. Now, there is other paper. This is a paper again from Sweden. This is Ghazal. They compared 10 machines. And this is much more modern. This is 2022 papers. So I just put you within 15 years of time frame, the papers which are published. And in this paper, again, I'm going to show you data for large fields and look at here the dose differences. Obviously, these are all 0.4, 0.4. This is these lines which you see is 0.5 plus minus 0.5. You see that the entire data sets are within plus minus 0.5% in these institutions for the 8 machines that they compare. And for 6 MV beam, 6 FFF, 10 MV, 15 MV beam, and 10 MV FFF. So there's not much difference. I mean, they are within the bound of plus minus 5%. When you look at it for the 10 by 10 field, those differences even disappear much faster. Actually, if you look at the 6 MB beam, the differences are within 0.2%. FFF even is also 0.2%, plus minus 0.2%. So you see this difference. So there's not much difference. So the question is that what to do? Well, this paper concludes that the high level of equivalency beyond clinical acceptable criteria for true beam Linux could be achieved, which reduced dose delivery systematic errors and increased confidence in interchanging patients among Linux. So if you have a true beam between one in the department, and if you are diligent, you could change the patient from one to other because it's just going to be within 0.2% or 0.5%. That's what the data indicates. Well, however, you still have to commission the data, and that's what I'm coming back. How you are going to commission, whether you're going to commission yourself or you're going to give it to the contractor. Somebody has to commission, and once you're commissioning, the only document, obviously it's an older document, it's a TG 106, and it may be worth your efforts to just read this particular document. Obviously, I'm not going to repeat a lot of this about the document, but in this document, we provided what you should be doing. You should be scanning. Also, you should be collecting non-scan data. You should be also collecting electron beam, photon beams, low energy, high energy, and all that thing. There are a lot of information that we provided in this. At that time, we also provided a time estimate. Obviously, at that time, we didn't had a smart scanners. These days, when you have a smart scanner, we computed at that time is that beam time is around 30 hours. That means 1 week. I mean, you think about that way. Typical time for commissioning is going to be 1 week, and whether you do yourself or whether you give it to contractor. Obviously, contractors they work day and night, and then they just get it done within 3 days or 4 days. All depends on that. Now, rationale for commissioning data is the manufacturing process at that time is not robust enough, like a Cobalt 60. It's a monoenergetic beam, and then you can just collect the data and then you are done with it. But that's not true for the linear accelerators, and there are changes taking place. Also, when they come and install that on the site, there are differences. Your engineer, they can tweak the beam energies and they may create a problem. Third, the beam characteristics of the soft wedges, the enhanced dynamic wedges, they are all based on the speed of your jaws, and that can change your certain aspects. And agreement between the golden data sets, it may be in a certain time that you might agree. And so these are some rationale why you must commission the beam data. The other thing for photon beam, that we use the flattening filter, and this typical flattening filters, but that's not what I want to show you. When engineers, they are assigned to your machines, when they come in the house, they tweak your beam parameters. Imagine if the fellow, he didn't pay attention, and if he let the electron beam goes in an angle, and it's just think about, you will have asymmetry. This is a perfect scenario when the beam is exactly coming on the center, and then flattening filter, you can see that beam is flat. But if it's not tilted, it's coming vertical, but it is off-centered, then also you will have this kind of skewness. So this and these are a problem. And so that's a beam tuning at the site becomes critical. And this is a part of the acceptance testing, that you should make sure that your beam is perfectly all right, and also depth doses are within your tolerance. So those are something that you need to think about. There's a very good paper, it was written in 2007 by Herbach. He provided a gamma index, and he was in the favor at that time that don't use the golden data because you might miss a lot of things, because you may just have on a central axis, but off axis points, you might just goof up, or it may not be possible to match all the beam parameters. And so we'll come back to this particular golden data or reference data in 2012, I wrote in favor of not using golden data. Obviously, there was a point counterpoint, uh, but I'll come back to this one here. Let's suppose that either you are taking data or your vendor is providing you the data or collecting the data. Then the question becomes that what kind of ion chamber you're going to use. Obviously, you have slews of vendors, slews of ion chambers, slews of things that you have to do. There is a standard chambers, mini chambers, and micro chambers, and you have to think about where and which conditions these chambers should be used. The other things too is that if you pay attention to the lots of chambers here, if you go to the small field, reference field and large field. So compare small field and large fields. You can see that depending upon your chambers, uh, there is a variations in the depth doses. And so the question is that if you're collecting data with not a proper detectors for 10 by 10, you may be okay, but for other field sizes, you may be wrong. And so you have to know the limits, which one you should be paying attention to. There are lots of detectors I'm not going to talk about. The other things too is that you have to be very careful about the connectors. And most of us, we are careful, but if you go to any department, sometimes you'll find that cables are broken or the connectors are not properly there, and it creates a problem. And we don't have a quality control on these detectors. You will find that if you actually pay attention, that sometimes the electrodes are bent, sometimes these wires are coming out, and so a lot of these things happen. The length of the cable also is a problem if you increase the number. So try to minimize the length of cable, because depending upon the quality of the cables, you can see that your readings are going to be dependent on the length of the cable when you have in the beam. So that's another criteria. We just wrote this paper about the investigation of triaxial cables, and especially for small fields, because you know that signal is very small, and when you have poor cables, then it just overwhelms the signal to noise ratios, and it becomes a issue. And especially if you see here that for a small fields in this region here, depending upon the cables and combination of the detectors, you can have a very, very large differences in your signal. So you have to be careful. Now, when you are setting the water tank, obviously these are all the standard common sense things, and these are all your board questions too. That when you are setting your ion chamber, uh, where you should set, whether you should set here, 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 because if you go up and down and you look at from the side of the tank, you may see these kind of diagrams, and the right choice is that if you know that your detector is a circular, then this is the right time when you. So that means the center of your detector is at the center. So that's something, that choice that you have to make. Electrometers. That's another caveat that people don't pay attention to, is the warm up. You must warm up electrometers, electronics things, and so also the null setting. We are in rush. You should set the null setting. Every electrometer has the null setting. Also, every electrometer has cable noise subtraction. So please do that too. Proper bias, I think it's a common sense, but everybody in their lifetime have done some goofy things. Um, in old days, we used to have a diamond detector, which was $8,000 at that time. It used to apply 100 volts. Now they have become 0 volt. But anyway, people have burned that whole $8,000 detector without anything. So just pay attention to the voltage. Sometimes the electrometers, they reset themselves when you turn them off. They reset the voltage, but some of them, they just keep the voltage. So make sure that before you connect, the voltage is either set 0 or that. Use the proper gain, proper mode, obviously charge mode, current, and then the range, because whether it is nanocoulombs or picocoulombs, and so that becomes a problem. Also, the suitable cable quality, as I mentioned to you, that the quality of the cable has to be very, very important. And why the cable quality is, here is the, when you are scanning the beam, and when you see some kind of a strange character, that means something is wrong. Either your gain is wrong, cable is wrong, or something. So just pay attention to the abnormal signal which is coming out of that your scan in the beginning. So that's something to think about. Other thing is that the choice of your direction, how you are doing. Uh, Obviously, any detector other than the spherical chambers, there are three orientations: this vertical orientation, X orientations, and Y orientations. And one has to pay attention to where you are scanning. Obviously, if it is a small, very, very small detectors, then you don't have to worry about these orientations. But in general, most detectors have a finite size, volume averaging takes place, and then you have to worry about that. These are all the from TG106. If you actually look at the different detectors, if you're scanning in this direction, you see the profiles will look something like this, which is not good. But if you're scanning in this directions, the volume averaging will be reduced, and then you'll see the same. So just to pay common sense things, that which directions you're going to scan these. The other thing is the setup. But water tank, when you are initially setting it up, the tilts, the angles, and all that. Now the modern scanners, they all have a built-in. They can detect whether your tank is right, whether your gantry is correct, whether. So the gantry and tank, they have to be properly aligned, and then you have to worry about those aspects. So just pay attention to that, whether one side tilt, the others, those kind of, when you see abnormal situations, then just look at it. Um, Another thing is the polarity. Most of us, we don't pay polarity. We just set up plus or minus, and then we just, so if you go through the depth and ratios of the PDDs plus minus, you can see that some detectors, they have a large differences in the polarity. So that's another problem, that you have to be consistent with your measurements, that use the proper voltage, proper bias, and then that you need to go through. Polarities in a small field becomes even much more critical. This was a paper from Lowe's just a few years ago written. And orientations, as I mentioned earlier, it also makes a difference. So the plus, minus, and orientations changes whole thing. And he provided a very good explanations why these things are happening. You can just read that. Other things too is that don't believe anything you measure from these detectors when you are scanning about the buildup or surface dose. No detector can give you surface dose properly, because you can see the surface dose is here and all these detectors are giving you, because um, there are lots of issues. The water, the buildup, the volume averaging, and so surface dose you should never take from your scan beam data. That's another observation. Scanning speed, that's another issues that you must pay attention to, especially for small fields, that if you see with the perfect condition, and if you see your depth doses are coming some jagged like this, immediately it should come to your mind that my speed is very different, because a slight change in water ripples changes the whole depth dose patterns, and this is a typical diagnosis for electron beams and all that thing. So those are the things that you need to think about. Speed, as I said, that if you don't set a proper speed, and there is no magic other than knowing your tank and knowing your system. You should scan with the low and high speed. Obviously, everybody wants to save time just by scanning fast, but you have to have an optimum choice where you're going to and how you're going to speed up and how you're going to reduce that process. So that's something to think about. Sometimes people say, well, don't worry, I'll just smooth it. And I think our recommendations are that don't smooth any data unless there is some major problem, because what happens that when you are smoothing data, the details of the beam characteristics, they changes, and so don't smooth unwanted. And here is the example. Here is the example that if you are smoothing, especially the wedge data, you can see that you can distort your wedge data quite significantly. Everywhere you will distort depending upon your smoothing. So minimize smoothing and just try to keep your data as good as clean as possible. Now, there are other things that you need to pay attention to. One is the diagonal scan. Most of the beam modelings are done through the diagonal scan. And in old days, it was very difficult because the software was not robust enough to uh, make a diagonal scan. But I think now modern tanks, they can do all that. You could also you think about that way, that large fields, and also you have to have over scan 5 centimeters on each. The tanks may not be sufficient length or width, and so you may have to do the half scan and then mirror them and all that thing. We recommended at that time that don't rotate the collimator, rather you are supposed to rotate the tank, and that becomes a problem. And that is not what most of the tanks can do. But I think nowadays modern tanks, they can take a diagonal scan without much of a difficulties. The small fields, so that's another kind of worm. TG106 has not provided much data because we didn't consider a 3 by 3 lower than 3 by 3. TG155 and TRS483 has provided some set of information about this. Obviously, the selection of detectors becomes critical. Signal to noise ratios are important, and again, scanning orientations because of the volume averaging is important. So that's thing. The TBI and total scan, again, the length of the cable, detector, energy, scatter, there's a lot of those things that you have to pay attention to. And as I showed you the data from TG106, that especially when you are taking the large set of data, there are many, many issues. One issue is that the scatter component hitting the electronics of the machines, especially the Sun Nuclear, their entire electronics sitting on the tank itself could create a problem, especially with certain detectors. Even for other ones too, you keep close to on the table, and then that could create. So you may have to. I mean, if you want to avoid, you may have to shield those detectors, because the signals, either small or large fields at the great distances, they are all at quite a bit of a low and then in pico, and then you need to just preserve the signal as much as you can. The head scatter, these are all just simple things in bread and butter. Old days, we used to do that. We still do that, but still there is an art to measuring this head scatter, total scatter, wedge factor, tray factors, MLC, DLG, transmissions, electron counts, virtual source positions. There are a lot of things you still have to commission. For some treatment planning system, you don't need the virtual source positions because the Monte Carlo based, but it's still validations you may require. And some of these things may be dependent on your treatment planning systems, and you need to think about that way. When you are measuring buildup, the most of us in old days, we used to think about just use the uh, lucite or perspex buildup caps. But then when you change the energies, then this becomes impossible because the fill size will become very, very impossible to measure. And in that situations, either use the high density or this is actually the mini phantom. And some people prefer the either aluminum or copper. The moment you use the aluminum or copper, I would caution you to read this paper, Weber's paper, and they showed that for a metallic materials, the deviations are that differences are significant, especially for high energy. So if you use a lead brass, there are going to be consequences. So you should just pay attention to the build up cap when you are using with this one. You could use the mini phantom, which the Tim Zoo's task groups they have provided uh, data in that regard. For MLC, follow TPS recommendations. Not everybody, we can't give you all that what you need to do, but estimate intra and interleaf leakage, estimate groove and tongue effect, and fine-tune leaf gap for match the TPS. This is a big problem because even though you measure, you may have to fuzz your data because you may have to come up with the right choice for. And a lot of times it's easier to do these things by using films, but there's not. I'm so sorry. So going back to magna field, if you are not, everybody does not do this total skin or total body. I think you have to pay attention to the details. And I think the total body, I think it's switching over to the VMAT. Most places they're following the VMAT. Then all these issues are mute. But if you're going to do the traditional extended distance, 4 meter or 5 meters distances, the detector response is important. Signal to noise ratios are important. In this one, extended distances, the Bremsstrahlung has become issues. I wrote a paper, oh my God, it's 35 years, 40 years ago, and um, that has been debated now, and there is a lot of discussions about the Bremsstrahlung issues in this aspect of it. Coming back to the small field, I'm not going to spend much of the time. Uh, Small fields, there's an uncertain dosimetry, obviously. There's a lot of uncertainty about the data collection. Modeling is also a big issue because most of the treatment planning systems, they only model up to 3 by 3 or 2 by 2. And the definitions, there are a lot of literatures on the small field, so I'm just going to leave this just for sake of this beam data things. FFF beams are also a issue, and the best reference I can give you is this Fogliara's paper. She wrote in 2012 a very, very comprehensive paper about where you should define the flatness, what should be your field size, what should be the. There are a lot of informations in this paper that you should read it, and you should just follow this paper about FFF beam. Now, what about the future of the beam commissioning? Obviously, you see that you're going to spend fair amount of time, and then you are going to say, well, why I'm going to waste time on the commissioning data? And machines are becoming just as good as possible. So Varian has decided to provide BRB, which is the Varian Reference Beam Data. They don't call it golden data, they call it BRB data. And as I showed you several papers, Ghazal's paper and also Glidehurst's paper, the differences between one true beam to the others are within 0.3, 0.4% plus minus in that regard. So if your tolerance is that, you may be able to utilize that, but still somebody has to collect the data to make sure that data falls within the BRB. For small fields and SRS, George Ding is providing the Monte Carlo based small field data, which is still some people may not agree that Monte Carlo can do that, but that's what it is. Newer radiation detectors and cables, micro detectors with high fidelities are available. For example, the standard imaging, the W2 plastic scintillators, I think they're the very, very good. Another thing is that the beauty of the newer scanning systems. The newer scanning systems, they have built in a lot of algorithms, and the softwares are capable of putting in the queue a lot of things that which I described is already built in. And so if you know how to deal with it, you could save significant amount of time. And so the newer software certainly is worth your investment if you're going to just do the commissioning yourself. So coming back to, and I just said, promise that I want to take questions because it's important for me, for you. So understand time and amount of the data to be taken. This is something very critical that you should not say, well, I'm just going to do the golden data. It's somebody has to still do the commissioning, whether you do it or the variant do it or whatsoever. That's not the case. If somebody has to commission the machine. So discuss with your administrations the timeline and cost associated with it. I mean, obviously, if you're going to do it yourself, you'll take months. If you're going to give it to somebody, they're going to take a week, but still you have to validate your data. So you have to know the timeline and how much money you're going to spend on that process. Reference data, in old days we used to call it golden data, then reference data. Reference data should be taken as a reference only. You cannot just say that, okay, I'm going to use it. The other aspect is that the reference data are only available by the variant for TrueBeam, and no other vendor has any reference data. So you can't use this for any other machines, any other reference. And so that's another problem. So if you have other machines, I just said that not all other vendors provide the reference data. So the contractors or vendors provided data must be verified. Whether you do it yourself or contractor do this for you, you must verify the data. And I think I showed you in the very beginning, all that why you need to verify, because you need to make sure that the treatment planning and then the monitor units and all the parameters are all kosher and they are good enough. So verify BRB data. This is important because if let's suppose somebody said, okay, just use the BRB. Well, I will not recommend you to just use the BRB. Rather, you have to validate. And I can come back to the previous slide that you have to verify, and the verification will take time. You cannot just assume that I'm just going to use that. And obviously, the moment you're going to verify anything, if you're going to set up the tank, you're going to do that, you have to use the proper techniques as described in TG106. I think other thing is that when collecting data yourself, this is another world of wisdom. Have a second physicist available to check your setup and beam parameter. Never do everything solo, because we all make mistakes. We are tired. We are in the evening, late night, and something can go wrong, and then you will be just liable for that beam data. So never have solo setup collecting data. So just have another physicist with you. That's the one thing. Proper detector for each type of data collections. I showed you or emphasized you that the choice of detector is critical where you should collect the data and what are the limits of those detectors. Set up optimum speed. Never rush for that. Do not rush. Just set up the correct speed for your time. And the most important thing you can do to yourself is that anytime you see any data which is not looking correct, any unusual data, just repeat it either same night or in the morning, come back. Do not smooth data as I wrote. And then the most other thing is the people just collect the data, they leave aside, they never write any report. It's a good idea, it's a good practice to put everything in a document that this is what it was done for future reference because you may not be there, somebody else will come and then they will question what happened to this data. And then this becomes litigations. The lawyers, they might just create that. So just don't put yourself in that situation. So just have the report properly. I will conclude this. I know that I rushed too much. I can spend fair amount of time on these things, but it's a good to just have a dialogue about what your thought process is about the reference data, golden data, and all the things that I said broadly. And I should be able to give you my opinion, whether you agree with me or not. But that is the dialogue that we want to have it. I don't know how much time left for the. Oh, we still have 10 minutes then. 10 minutes. So thank you very much. Again, this is Sunset at Chicago. And so, Ashley, if you have questions, I can answer anybody. Or if anybody has a questions, you guys free to call me, send me email. You can find me in AAPM or Ashley can send you my email. And if you don't have time to ask questions this time, but I would like to take some questions at this time.
Absolutely. Thank you so much, Dr. Das, for such a wonderful presentation. It was so thorough and so informative, and we're so grateful for you presenting on that. If you have any questions for Dr. Das, just submit them using the Q&A module at the top of your Teams screen, and we'll go through them in a moment. Just one reminder that we will send a recording of the presentation, including the questions this week, so just keep an eye on your inbox for that. Our first question, what is the reason for variation in depth dose at larger field size 40 by 40 for different detectors?
Yeah, so there are two questions immediately that stuck to you is that the type of detectors, and that becomes the mu(n) over rho values of that type. And you know that for large fields, the the spectrum is different. And since the spectrum is different, the response is different. That's one. The second one is the signal to noise ratio, especially if you're measuring in picocoulombs, depending upon how small your signal is. So the materials and the signal, those are the two aspects that changes. The volume averaging is not there because your field size is very large and you don't have to worry about. So when we talk about the spectral response, so for example, the diodes, they have an energy response in the diode. And so if you're using the diode, you will have a different response. Ion chambers are preferred because we know that mu(n) does not change as much. But again, then you have to worry about the electrometer selections, the range selections, and then response. That's one. The other thing is that there are recent papers that they provide data indicating that if your electrometers, if it is sitting in the room, they catch up data. I mean, they catch up the signal. And so if you want to do that, you have to shield your, it will be problematic, but you have to shield your electrometers with the lead blocks or lead shields. That will be for some it is possible, but some it may not be. For example, the sun nuclear, it may not be a possibility.
Thank you. The next one is, what would you say about the reproducibility of beam for Versa HDs?
Very good question. I obviously the Versa HD or the Versa are they are of a different vintage. They are different types and uh, reproducibility. I think I'm not expert on the Electa machines, but I mean they are good machines. But reproducibility will be a questionable because I had here four machines and they were all different. They were not. We cannot match the beam. So it's very hard for me to comment on that, whether these machines are all identical. You may have to refer to the Electa people that whether they are reproducible or not. My gut feeling is that they are not because they don't make that many machines.
Thank you. The next is, what is your opinion slash suggestion on using IC profilers instead of 3D scanning water tanks for validation? Thank you for the brilliant presentation.
Yeah, that's a good question. I think there are several papers in JSEMP and people have attempted. You have to try. The problem with the IC profilers are that they are all size. The size is 20 by 20 only, and when you are doing the validations, you still need 30 by 30 field size. So up to 10 by 10, I don't have any problem there, but beyond that, I think I will have questions whether the data are accurate or not. And especially when you're doing validations, you're going from one lower field to the higher field. So at least you have to validate for 30 by 35 by 35. So I don't know how you're going to do it with this 2D devices.
Awesome, thank you. Dr. Das, what are your thoughts on overlapping beam data collection across a few shared field sizes, examples 3 by 3 or 4 by 4, when doing small field dosimetry measurements with a microchamber or diode detector?
Good question. I think you should overlap. I mean, I think it's a good idea to overlap. You know, the daisy chain process is overlap process. And so if you have a detectors, if you're going to measure, um, 2 by 2, 3 by 3, 4 by 4, and then you can repeat the same thing with the small fields detectors, and you can just, so if your datas are looking good, then you can just, so I think that's how daisy chain process works. So you are just doing a daisy chain uh, process, and it should be a good options.
Wonderful, thank you. Can we repeat commissioning every time? If yes, what will be the consequences on treatment?
Repeat every time. When what do you mean by repeat every time?
They say, can we repeat commissioning every time? If yes, what will be the consequences on treatment?
Well, you're commissioning machine only once. What's unless your waveguide or something blew up, and you commission machines when you're installed, uh, but you are doing annual calibrations. So the annual is mini commissioning. So if you meant by the mini commissioning, you just take sample the field size and data, but I don't think that you will be repeating the commissioning every year.
All right, sounds good. Thank you. Last
Yeah.
one that we have here so far. How much setup error is acceptable in a 6 by 6 millimeter field size? If the profile is having a shift on MLC direction, is it because of MLC or setup?
Good question. I think MLC, you should verify yourself with the film or with some other independent process. So you have to eliminate one versus other. So first you eliminate whether your MLC is repeatable. Um, Chances are the modern machines, the MLCs are very, very reproducible because they are hardwired. They are actually coded. The positions are coded. That is correct. So if you see something, uh, chances are that it's your setup that is happening. But again, when we are talking about 5 millimeter fill size, over there, even a fraction of or even a 10, 15 micron can change a lot of reading. So you have to rethink about that aspect of it. But it's not a simple answer. You have to think about the uh, going both ways. First, eliminating your MLC issues and then your setup issues. Whenever you are doing these setup issues, depends on the what kind of a field size you are taking. For example, when you go to the 5 by 5, obviously they're all symmetric. So you'll find that 5 by 5, you can't make it 2.5 and 2.5. So it will be one side will be 2, another side will be 3. And so if your ion chamber is set up at 2.5, you are obviously going to not see any the peak signal. So you have to just find where is the peak signal. So you have to scan that thing. So you have to use a common sense sometimes and work accordingly.
Perfect. Thank you. That's all I'm seeing right now. So if there's any last questions, please get those submitted for us. One came right through. If the radiation field and field light differ in size, could the field light be mispositioned, in parentheses, position in the beam line?
So the radiation and light fields are only for reference conditions. That means for 10 by 10 and all in the conditions where the electronic equilibrium exists. For a small field, the radiation and light fields are misnomer, and they always have a different definitions, and that you have to go back to my paper in 2008 paper on a small field. So uh, cannot trust light and radiation field uh, for a small field. Those concepts were only developed for the reference conditions.
So, that's all that I'm seeing. So guess if you have any last minute ones, submit them. But otherwise, thank you so much again, Dr. Das, for such a
Thank
wonderful
you.
presentation. And
Thank you.
thank you to
Thank you.
everyone who joined us.